There we go. All right. Strategy one for dealing with alcohols and using them in substitution/elimination reactions is to turn the OH into a good leaving group by protonating it. The problem we said with that is that you usually go through a carbocation intermediate. And so if you've got stereochemistry to lose, as is the case with this chiral alcohol, you are going to get both enantiomers because you go through a planar carbocationic intermediate. And that's not the only problem. We started talking about a problem that's actually been going on the whole time, but I didn't tell you about, and that is the dreaded carbocation rearrangement. So I gave you this example where you have a quaternary carbon next to an OH group. We protonate the OH group, and then we saw these products where in one of them the bromo is in the right place. In the other, it looks like one of the bromos and the methyls have traded places. And the mechanism for that starts with a planar carbocation and an adjacent sp3 hybridized carbon. Hyperconjugation allows the methyl group, the electrons in the carbon-carbon bond with the methyl group, to donate partially into the empty p orbital here. This is the plus combination of hyperconjugation that we've talked about. Gradually, that methyl group can lean over and you go through a transition state that looks like this, where the methyl group is sort of evenly between these two carbons. You have 2 electrons shared between 3 atoms. And that seems weird, except it's not that weird. You've seen situations before where 2 electrons were shared between 3 atoms, right? In resonance. So here is the transition state, and as the methyl group starts to lean over even further, you make a full bond here. Now, we were going to talk about what might be the driving force for this. What do you notice? What changes after this rearrangement? Aside from the fact that the methyl group moves over. Go ahead. More substituted carbocation, good. This is a tertiary carbocation, whereas we were starting with a secondary carbocation. So you might predict that the tertiary carbocation might be more stable, and that's the driving force for this to happen. Now, I'm not going to ask you to choose which of these is the major product, because frankly, unless you do the reaction, I'm not sure you know. Sometimes your text will act as though the rearranged product is the major one. And instead, I'll have you just draw both of them or choose both of them as answers rather than decide which one is the major one. I'll only ask you to consider carbocation rearrangements when you go through an intermediate where doing a rearrangement would lead you to a more stable product. For example, a tertiary carbocation adjacent to a quaternary carbon. That's a classic situation where you can get carbocation rearrangement. So watch for that. Another situation where you can get carbocation rearrangement would be if you had a tertiary carbon adjacent to a secondary carbocation. Then the same sort of thing can happen. Let's see, tertiary carbon, secondary carbocation. You've learned that the proton that's beta to the positive charge is already hyperconjugating into that empty p orbital. It just leans over completely, goes through that 3-atom, 2-electron sort of transition state, and this is how you draw the mechanism. You simply take the electrons in the bond between carbon and hydrogen and have them move over. And that gives you a more stable, more substituted carbocation. Now, you'll notice I made a choice there. I could have had a methyl group move over, or I could have had the proton move over. Why did I choose the proton? Go ahead.
It's less sterically hindered.
Okay, a proton is less sterically hindered. How about, what would the product, go ahead.
When you leave the methyl groups on the other side, it keeps it a more substituted carbocation.
Bingo, good. So if I had moved over a methyl group, that would just be trading one secondary carbocation for another. If I move the proton, I can trade a secondary carbocation for a tertiary carbocation. All right? So that's the other situation where I'm going to ask you to think about carbocation rearrangement when you have a secondary carbocation. Whoa, sorry about that. I'm going to sneeze now. Phew, excuse me. You know, I have a brother-in-law that does sneeze impressions. It's actually pretty funny. He's learned how members of his family sneeze, and on demand he can do sneeze impressions. Kind of gross in the post-COVID era. We've learned that sneezing is offensive, so I'm sorry. Okay. So those are the two situations where you need to expect carbocation rearrangement. Now we're going to use that as motivation for these other synthetic methods I'm going to show you for doing substitution reactions with alcohols. However, I want to pause to show you some interesting biology that involves carbocation rearrangement. As always, I'll need to issue the disclaimer that I don't expect you to memorize stuff. But I want you to understand what's going on. Let's see, I just want to illustrate what we just talked about in the sense that you would get the rearranged or the not rearranged product and the rearranged product. Okay, so carbocation rearrangements are all over the place, particularly in the biosynthesis of what are called terpenes, and these are nonpolar natural products that are found in a lot of essential oils and fruits, and for example, the smell of citrus comes because of a terpene. I want to show you though a much more complicated situation that's involved in cholesterol biosynthesis. And you'll probably come back to this again later on, maybe or actually we will come back to this again because we're going to talk about how you even get to this molecule in the first place. By the way, that's why sometimes we talk about decalins, because a fused 2 6-membered rings are part of cholesterol. There's some other functional groups here. This is a precursor to cholesterol. It's not cholesterol itself. Are you feeling nauseous yet? Okay, yeah, make sure you memorize that. Which of the following is cholesterol? This isn't even it, so. All right, so what I'm going to draw is an intermediate in cholesterol biosynthesis. It's got a tertiary carbocation, and this is called the protosterol cation. Before we're done this semester, you're going to be able to push arrows that take a linear precursor and get you to that. Wow. It's actually easier than you think. The place we want to get to after the carbocation rearrangement is this. So let me draw the whole thing again. I'm sorry to spend all this time drawing, but I feel like the payoff is worth it, so just hang in there. All right, there we go. Okay, so what do you think? Let's take a look at what's happened. And I want you to actually, before we do that, look at how carbocation rearrangement happens. Did you notice how the methyl group went over on the same side of the molecule? It's not like it twisted and was delivered to the bottom side. You're going to see that in general with carbocation rearrangements. And I guess I'll just point out, people call, because people sometimes try to find shorter ways to say carbocation rearrangement. They'll call what we did first up here where a methyl group moves over a 1,2 methyl shift. They'll call this one a 1,2 hydride shift. That means a methyl group or a proton with its electrons move over from carbon 1 to carbon 2. But notice how that happens on the same face of the molecule. We have a word for that in OChem. It's not important, but I'll write it down anyway. Suprafacial. That means it happens on the same face. So I want you to pay attention to what's moved as we get from here to here. What do you see moving? Go ahead.
Sorry, just quick question.
Yeah.
It seems like you're talking about how most of the time it happens on the same face, but it can't happen on it. Like,
For a 1,2 shift, it's always on the same face. Yep. All right. So what's happened? Go ahead.
So you talk about how you can rotate around the single bond. So can you explain why the shift stays on the same face?
Oh, sure. How does the shift stay on the same face when you can rotate around this bond? I'm not saying you can't rotate around this bond, but I'm saying that in order for the 1,2 methyl shift to happen, there has to be continuous in-phase overlap. So as it happens, what I'm saying is orbital symmetry requires it to be delivered across the same face. Now, I agree that this is going to happen also if we rotate around the bond and the methyl group's over here and the proton's there, for sure. But during the transition, it has to happen from the same face. So what do you notice? Where does this proton end up? Go ahead. Yeah, other issue. Go ahead.
No, I was going to answer your question.
Okay, please do.
Oh, okay.
Proceed.
It looks like the proton just shifts on up a little bit.
Right, and it looks like it did so on the same face, right? Because it was down here and now it's down there. Yeah? So we can show that 1,2 hydride shift by simply taking that hydrogen with its electrons and walking the proton over. Okay. So we need to keep this as our goal where we want to get to. And I want to show a potential intermediate that happens after that proton moves over. And remember, it's got to move over. Whoops, I need to change the color there. It's got to move over on the same face. All right. Now compare again where we need to get to. What do you think happens next? Another one. Go ahead.
Looks like hydrogen that's pointing into the page on the top shifts over.
Another one, right? Another 1,2 shift. Okay. And notice how these shifts take a tertiary carbocation and they convert it into another tertiary carbocation. I'm not going to ask you to predict carbocation shifts of that kind. However, you should see that they're reasonable in the sense that you trade carbocations of similar stability. Yep. Is that them hopping along the way? Yeah. So then we're going to continue to do these shifts one after the other. For example, I'm not going to, well, maybe we'll copy and paste. And actually, when people draw these mechanisms, frequently they don't actually draw these intermediates. It's not clear, based on the free energy landscape of this situation, whether these happen via individual steps or whether they sort of happen in the same step. It's the difference between an energy diagram that looks like this versus one that looks like this. And so some people feel like this energy landscape is pretty broad, and so that all of these, without a lot of peaks or transition states, so that all of these intermediates, all of these carbocation rearrangements happen in a cascade that's connected to the other. So you can sort of see where we're going with this. We're going to have this methyl group lean over and go there. And then if we make that carbocation, we're going to have this methyl group lean over and go there. Yeah?
So are we just to kind of assume that, like, if these shifts can occur, they will? So, like, if we do, if we're changing the OH into a good leaving group with hydrochloric acid, hydrochloric acid, like, we just always assume the cation can have, like, that sort of shifting.
So, yeah, the question is, when do I think this is going, when are we supposed to know when this is going to happen? And the answer is, I'm only going to ask you to predict that it happens in a situation where you have a secondary carbocation adjacent to a quaternary or tertiary carbon. Those are the situations where I want you to be able to predict that it would happen. What we're doing now is an entirely different thing. This is like a mechanism question. So if I show you a starting point and an ending point and a carbocation rearrangement is required, I'll expect you to be able to determine where and when that occurred. All right? So the intermediate we get after that 1,2 methyl shift puts the up methyl group on this carbon. And then we do, let's see, a positive charge here, and then we'll do one more 1,2 methyl shift, and that will get us to the desired carbocation. Okay, so let's see, I'm counting 1, 2, 3, 4 carbocation rearrangements. Boom, 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 boom. Yeah.
Why does it stop right there?
Why does it stop there? It could go further. Don't know, other than this takes place in the context of an enzyme. And so this is a hand-wavy explanation, so when I say that, I mean I don't actually know the answer, but I'm hypothesizing that the reason it stops there is because there's a side chain in the protein that can act as a base to do the elimination of this beta proton. Yeah. And once that elimination occurs, you get a precursor to a lot of different steroids and cholesterol-derived molecules. Has a double bond here, and this is called lanosterol. And it's actually 19 more steps to get from lanosterol to cholesterol. So we're not going to learn those. But this is a common precursor to, and I wish I had maybe drawn some of these for you. Let me check and see whether I even have. Nope, sorry. This is a common precursor for estradiol, testosterone, progesterone, steroid, anti-inflammatory steroids, cortisol, prednisone, cortisone. Vitamin D actually comes from this synthesis too, and then bile salts also come from this. So tons of different molecules, all from this carbocation rearrangement process. What's really wild is it's taken us, looks like 10 minutes to talk our way through all of this, and in the meantime your body's been cranking at this really, really fast all along. Okay, so why should you care about carbocation rearrangements? Because you are doing them right now. Right. So let's talk about other strategies for turning the OH into a good leaving group. And these are strategies that do not involve carbocation rearrangements. Avoid carbocation intermediates is the next strategy. And for this, we're going to introduce some useful reagents. When we introduce new reagents that do specific things, sometimes there's not a good theoretical explanation for why they act the way they do. In some cases, it's simply an empirical result. But in OCHEM, we're willing to accept empirical results if they allow us to do a useful synthesis. So what I'm going to show you now doesn't go through a carbocation rearrangement, and you're going to ask me why not. And I'm going to give you an explanation that is more of a mnemonic device than it is an actual explanation. And you may have to be content with not knowing why it goes this way. All right, so let's take an alcohol like this. And we'll use a reagent called PBr3. That's weird. That's phosphorus, which we don't have a lot of experience with, bonded to bromines 3 times. And what this reagent does is it replaces the OH group with a Br, and you get inversion of stereochemistry configuration. So that is a clue that if there's inversion of stereochemistry, that's a clue that there was an SN2-like step along the way and that there is no carbocationic intermediate. Okay, now the mechanism I'm going to show you, your text has, I don't think, there's a lot more important things. I'd rather actually ask you questions about carbocation rearrangements than about the mechanism of this reaction. So what I'm going to show you, you can consider is just sort of for your personal edification. I won't ask you a question about this mechanism. PBr3, it turns out that oxygen-phosphorus bonds are actually quite strong, and so that's going to be one of the driving forces of this reaction. The oxygen attacks the phosphorus and, and displaces one of the bromines, and you get an intermediate that looks like this, in which you've made a new phosphorus-oxygen bond, and in the process you've converted OH from something that was not a good leaving group to something that is now a much better leaving group. So all of this is now a good leaving group. And we could try to look up the pKa of that group's conjugate acid. We won't worry about that. As I said, I'm not going to ask you to draw this mechanism, but once you convert that into a good leaving group, then Br minus can come in from the backside and do the substitution chemistry in an SN2 step to give you the bromide product. Now, this is the step you might be uncomfortable with, because the question you can ask is, hold on, if this is a good leaving group and this is a good leaving group, why is it that water can leave but that other good leaving group doesn't? I don't know. I got nothing. Okay? I could say, well, maybe this is slightly less of a good leaving group than water, but I really don't know. And I'm not actually sure. Your text certainly doesn't explain it, and I'm not sure anybody's explained it. So if you want to go in the lab and try to figure that out, more power to you. Again, though, because it works, the synthetic organic chemist is going to say, shoot, that's a useful reaction, and be willing to use it even if they don't understand quite how it works. And the way reaction discovery works in OCHEM, you first discover a reaction, then you try to figure out the mechanism, and that sometimes involves calculations. But even if you don't know the mechanism, if the reaction's useful, people will use it. Yeah?
So what makes this reaction useful?
This reaction is useful because it turns OH into an alkyl halide, which is a much better leaving group than OH, and it keeps stereochemistry part of things, right? We don't go through a carbocation intermediate, so we don't lose stereochemistry. All right. So there's an analog to this one in terms of substitution chemistry with chlorides. So we can take the same starting material and use a reagent called SOCl2. I'll draw what that looks like. Sulfur can have more than 8 electrons around it, just like phosphorus can. This gives you the corresponding chloride, again with inversion of configuration. The mechanism for this reaction is I could draw it for you. It's much like this one, and I don't actually think it's worth knowing, so we're not gonna. You'll see, I think, I'm trying to remember in your text that often with SOCl2 they include a base that's not a good nucleophile called pyridine. Here is the structure of pyridine. You don't need to memorize it. Presumably that's because, and I think the mechanism your text will show involves an intermediate like this, and then pyridine will act as a base to remove this proton prior to the leaving group leaving. Now, again, this is an issue that I'm not going to ask you to worry about. You can ask me, why is the base necessary for SOCl2 but not for PBr3? I don't know. You might also ask, if this is a base, why doesn't it do elimination chemistry? And I'm going to say, I don't know. So we're in a situation here where you may have to memorize that SOCl2 converts an alcohol into an alkyl chloride, and that it does so via SN2. And because you understand what SN2 is, you'll know to expect inversion of configuration. All right. Questions so far? Yeah.
So do you actually want us to memorize that?
I don't want you to memorize the mechanism. I do want you to know the reagent, yes. Now, how can I ask a question about this? Excellent question. I'm glad you asked. So you can do predict products questions where this is a very simple predict products question. What is the reagent that makes that conversion? And you'll have options A through Z, and one of them will be correct, and that's PBr3. Where's the inversion? Boom. There it is. Sorry. Also, I could make it slightly more complicated. I could say, take this alcohol and turn it into this product. And I'll give you a hint, you can't do it in one step. Any proposed strategeries? Yes?
So you first use the PBr3 and the imidazole bond as backside attack.
Okay, so you want to first use something to do one inversion. So the intermediate after step one would be the thing we drew above, right? Then what? Except. Bloop. Thank you. Then what?
And then, is that imidazole, NT?
N3 is called azide. Yeah. N3 minus as a nucleophile doing an SN2 type reaction. Good. All right, and this is a decently simple synthesis. When you're doing a synthesis, you have to look at first what overall change are you making, In this case, I'm replacing an OH group with an N3 group, but I have to know, whatever I do has to account for the fact that the stereochemistry is the same. You see that? The OH group was up, the azide is up. That tells me I can't do that via one SN2 step. If I did it via a simple SN2 step, first of all, OH minus is not a good leaving group. Second, I get the down version of that azide instead of the up version. So I needed 2 successive inversion of configuration steps. Does that make some sense? Yeah? Okay. Right. What if, I know you guys like to, in the dark of the night, play the what if game where you start to worry about your future and what if this happened and what if this happened. So I'm going to give you something else for your nightmares. I actually am not awake in the middle of the night worrying about things. I have a CPAP device for my sleep apnea, and that thing goes on, and I start breathing like Darth Vader, and I'm out. It's just fantastic. All right, anyway, what if let's see, what if I did this? Whoa. Look at what's changed. I can tell that I've made this carbon-carbon bond, and sometimes when you're doing a synthesis, it's good to just think one step backwards. What was the last step that could have led to this product? We'll use an arrow like that. It's called I'm so emotional about this. This is called retrosynthesis, where you think one step backwards. And I'm imagining that if I could start with something like that and use this as a nucleophile, maybe I could do that reaction. But how am I going to get from here to there with the right stereochemistry? Go ahead. Okay, I could use SOCl2. Would that give me correct stereochemistry there? No, because SOCl2 is an SN2 reagent. You'd get inversion. So if I protonated the OH first, I'm going to go through a carbocation intermediate, and that's going to make it so that I get a racemic mixture, or rather I'm going to get, it wouldn't be a racemic mixture, it'd be a mixture of diastereomers where we have both configurations of this carbon. What you're really looking for is a way to convert the OH into a good leaving group without messing with the stereochemistry. Say that again? Tosylate. Yeah, if you've been reading ahead, there's a reagent that does this, and it's called para-toluene sulfonyl chloride. So unless you want to write that all the time, there's an abbreviation for that, TSCl. And the reagent looks like this. It's got a benzene ring, a methyl group. This is the sulfonyl chloride group. And basically it's got this pretty reactive, good leaving group on the sulfur. And so you can actually take this alcohol that we've been talking about and you can have the OH group attack the sulfur in sort of SN2 fashion, and the chloride leaves. Now, that's SN2 on the sulfur, not on the oxygen. The oxygen's the nucleophile. And so that will give you this intermediate. Now, apparently, this intermediate is not reactive enough for the leaving group to leave on its own. Nor is it reactive enough for Cl- to come in and do SN2 from behind. I don't know why. I really do not. And that's why these three reagents sort of go together, and you're going to have to memorize some of the outcomes of the reaction. So you get this intermediate. Usually with para-toluene sulfonyl chloride, you also include the pyridine base to remove the proton from this intermediate. And that will generate a shelf-stable product that you can store in the fridge and then use again at some other point in the future. And this is a reaction people do all the time in the lab. So this product, because people often do not like to draw out all of this, you're welcome to do so. They instead will write TS to stand for the para-toluene sulfonyl, and then with the oxygen there. This functional group would technically be called a sulfonyl ester, but we're going to call it a tosylate. That's an abbreviation sort of for para-toluene sulfonyl chloride. People will call this reagent tosyl chloride. Why do they call it that? Well, somebody took the TO, the S, and the IL, and they called that the name of the molecule. All right? So let me try to be a little clearer. To do this reaction, you would use para-toluene sulfonyl chloride and pyridine. That would convert the OH into a tosylate. I told you that the tosylate was stable and you could store it in the fridge, but it is also a good leaving group. The reason it is a good leaving group is because it is the conjugate base of a strong acid. So you can do SN2 type chemistry. The leaving group ends up being this. Okay, and this is para-toluene sulfonylate. It is the conjugate base of para-toluene sulfonic acid, which is another reagent that you will see at some point in the future. They call this TSOH, and it's basically the organic soluble version of sulfuric acid. So this is a strong acid, and this is the conjugate base of the strong acid, which means it is a good leaving group. Now again, you might ask, if it's such a good leaving group, how come it doesn't leave until you do SN2? Don't know. Presumably there's an explanation for that, but again, the organic chemist that's worried about synthesis is more concerned about getting the right product than all of the intricacies of how it actually works. And there probably is an explanation for why it doesn't leave. I just don't know what it is, and it's probably beyond the scope of an introductory OChem class. Yeah?
Is the chloride also reactive with that?
Yeah, that's another great question. There's chloride here. Why doesn't the chloride just, once you make this, do SN2 chemistry, and then you get inversion of configuration? Got nothing. It doesn't happen, yeah. Okay? So, there's some complicated issues here, right? PBr3 gives you the bromide with inversion of configuration. SOCl2 gives you the chloride with inversion of configuration. Somehow we need pyridine for SOCl2, but not for PBr3. If you've ever been in an organic lab and invented a reaction and tried to show how it works, go talk to folks from the Michaelis lab that do this all the time, or the Castle lab. You take a reagent and you're like, how can I make this reaction better? And you say, well, what if I added a base? And so you try a bunch of bases and you see which one gives you the best results, and then you use that base. And often you don't pause to ask questions as to why it works, just that it works. And if it works over a broad range of molecules, you just go ahead and use it. Then you can use paratoluene sulfonyl chloride and pyridine. Why does that not do the same thing as SOCl2? The players look pretty close to each other in structure. Again, I don't know. But the point you need to take from this, aside from memorizing the reagents and what they do, is the sense of strategy. Notice that here, I wanted to replace the OH with a nucleophile with just one inversion. So I needed to convert the OH into a leaving group that would, without touching the stereochemistry. And our strategy is to use the oxygen as a nucleophile with this reagent to change the alcohol into a tosylate, and then, and only then, doing the SN2 reaction. This only involves one inversion step instead of two. So there's some synthetic strategy going on. Practice this. I'm almost certain there's a practice exam question on this, and I can guarantee you that you will see stuff like this on the exam. All right, any questions you want to ask? Yeah.
So we're safe to assume that the chloride ion never like the SN2 with the tosylate once it's formed.
Does the chloride ion never do SN2 with the tosylate once it's formed? I cannot guarantee that as a blanket statement over the whole universe and for eternity, but yes.
Right. So I guess maybe just looking at like the end product, like if it were a chloride group, but then it was inverted.
Right. If the chloride attacked that, you'd get inversion,
Yeah.
and so you get the wrong stereochemistry of the product. Yeah. So I really am not sure why, because again, if you look at this structure versus the intermediate in SOCl2, the chloride does do this. One of the reasons for that, you don't want to know this and I don't want you to remember it, is that as soon as the chloride attacks, the whole thing falls apart and you get SO2, which is a gas, and bubbles off. So it's possible that this is just a spring-loaded leaving group that once you start, you're done. That can't happen with the tosylate, so yeah. All right, so we're going to make it worse with one more reagent. So you've got in the issue of avoiding carbocation intermediates, you've got strategy A with PBr3, strategy B with SOCl2, strategy 3, make the tosylate. Oh wow, we just changed. It's like Buzz in what is it in Home Alone, where he starts explaining reasons A, this 2, and D. So yeah, this should be C. Strategy D is the, I think, last of your memorized reagents for today, and unfortunately, it's the hellish combination of other letters that we have seen today. This reagent is POCl3, or some people affectionately refer to it as POCL. And you're also going to need pyridine for this. But POCL does something different, even though the players look similar. So here's your alcohol. And we're going to make this a situation where if we formed a carbocationic intermediate, we would expect to see some rearrangement, right? If this OH group left, we'd have a secondary carbocation adjacent to a quaternary carbon. We might expect a 1,2 methyl shift. With POCL, we don't get a substitution product, we get an elimination product, and we get no rearrangement. That means that presumably this reaction was E2 with no carbocation intermediate. Now, just as a preview, I'll show you the mechanism. I don't want you to memorize it, or I'm not going to ask you questions about it. You are going to ask why it does this instead of some other very reasonable options. And again, I'm going to say, I don't know. But your text is written from the perspective of a synthetic organic chemist. Professor Smith was trained in the lab of E.J. Corey, who's a famous Nobel laureate organic chemist at Harvard. And again, if your goal is to make stuff, you may not care why the stuff works if it works consistently. And this is a reaction that does. So Pockle is a reagent that looks like this. It looks a lot like PBr3, only it's a more oxidized state of phosphorus. And the mechanism is basically very similar. You have the OH attack the phosphorus and chloride leaves. That generates this intermediate with a positively charged oxygen that has a proton on it. You're going to use the pyridine as a base at this stage to remove a proton from the oxygen, and you'll get this intermediate. Oops. Drawn the wrong structure. This is now, again, we've done something to convert the OH into a good leaving group. We had Cl- leave. Again, why doesn't that come in and do substitution chemistry? No idea. What instead happens is you find a proton beta to the leaving group, and you use a second molecule of pyridine to remove the proton and do the E2 style elimination chemistry. Okay? So you're going to need to memorize that Pockle and pyridine give you the E2 product without carbocation rearrangement. Everything you've learned about the E2 reaction will apply to Pockle in terms of stereochemistry, the proton, beta proton needing to be anti to the leaving group. But our purpose here is to use it to convert the alcohol into a good leaving group and do elimination chemistry without rearrangement. All right, that's enough for today. I will see you next time.